Hello everyone, this is video from me, your instructor, Ekaterina Savchenko, and I'm going to do the first page of our tutorial capacitance. Usually, I don't know, the text is combined, like people never understand it. So in class, I usually just tell the students how to understand the questions on this first page. But because we are not in class, I'm just going to go over the questions and explain like how to solve them. If you have a tutorial with you, you can open it on the first page because I'm not going to kind of show you tutorial and kind of just solve it on tutorial. I'm going to give you like a lecture. So in the first question, they are giving us a portion of a center of a large thin conducting plate. What is actually conducting plate? Conducting plate is something which made out of conducting material. Conducting material has a property that electrons can move freely around the material. And if they do feel some electric field, they're just going to follow this electric field like a highway and move somewhere. So I'm going to start with a drawing, like a picture what they mean. So they have a conducting plate and they shade it like this, right? And they tell us that the net charge of the certain portion of this, we are looking like conducting plate is actually looking like this, right? It's looking like this, but we are looking from the side. And they give us some area, and this area, they label it as area 1, and it has a total charge Q1. And they are asking us to write an expression for a charge density on each side of the conducting plate. Well, guys, from the symmetry reasons, we're supposed to assume that the charge is going to be same on the left side and on the right side. So the density of the left side of this plate and right side of the plate is going to be same. We are not going to have any charge inside of the conducting plate because if we do have, this charge will move to the surface. Why? Because whenever you have a electric field, the charge is going to move along this electric field. So we are going to have electric field. If we do have it inside, the charge is going to move along. So we are going to kind of see that this is like sigma and total area is A1 and the total charge is Q1. So what I'm going to do, I'm going to write down that for the same area, what we know about sigma equals charge divided over the area, right? But because we do have the same charge kind of distributed half on this side, like Q1 over 2 on this side, and Q1 over 2 on the other side. So I'm going to, instead of using Q1, use Q1 over 2. So that's going to be the density on one side of the plate. Now they are asking us to use a principle of superposition and determine electric field inside of the conductor. What if we have the density like this, and what is going to be the how electric field is going to work? Guys, I'm going to draw a very general way to represent conductors, to represent plates. We already have seen this way in previous tutorials, but I'm going to repeat it one more time. And I just want to use a different color. So instead of drawing the plate like this, we are going to draw one surface like a vertical line and another surface like a vertical line. Again, you see that the gap between them is much bigger than on the picture. But if I draw it like on the picture, it's going to be hard for me to draw any electric field. We do know density here. Density here is like Q1 over 2A1. And we know density on this plate too, which is same, right? Q1 over 2A1. Now, we do remember that each of these plates is going to create electric field independently from the other one. This is the principle, that's a principle of superposition, that each electric charge creates electric field like he does not know about any other electric charges out around it. So I'm going to use a different color and maybe a little bit thicker draw lines. Okay, So I'm going to start with my left plate. I'm going to draw electric field. Well, I don't know. They don't specifically tell what the charge is, positive or negative. I'm going to assume that it's positive charge. I just don't see it. Maybe they tell it somewhere. But for the positive charge, the left plate is going to create electric field going from it, right? Something like this. On the other side, that's going to be the same electric field, and in here is going to be the same electric field. We remember that electric field is same near the infinite plate. If the plate is finite, has a size, it's not going to be same. But for infinite plate, the electric field is same on the left and on the right. Why do I draw two arrows on the right? Well, because there are two regions, right? I'm going to label them region 1, region 2, and region 3. Actually, my region 2 is inside of the conductors, this shaded part, but I'm not going to shade it here just because I don't want to mess it up. So what is going to be electric field here? Remember the formula we had the previous class or the previous tutorial, that electric field is equal to what? Electric field of something with density sigma is equal to sigma over 2 epsilon 0, right? It's going to be same electric field for all green arrows. I'm not going to label it everywhere same. I'm just going to tell this, okay? Now I'm changing the color to draw more arrows, and like from the right plate, from this one, which is sitting on the right. And because if you assume that the left plate is positive, the right is going to be positive too, because it's the same, right? And the field will go from it like this, and like this. Okay, my arrows do not look like they same size, but they must be same size, because I just told that the electric field is constant on each side of charged plate if it's infinite. So what is going to be this orange field? Orange field, according to the formulas we got on the previous one, on the previous tutorial, not on electric potential, but on the previous tutorial where we were doing the charge plates. It's going to be, again, sigma over 2 epsilon 0, right? Well, we're not going to plug in sigma yet. We're just going to first look at the net field. To calculate the net field, I'm going to use again a different color. Maybe I should use blue. And just draw a net field on each of these three regions. And that's how we usually do it if we solve it for exams, for tests, quizzes. So over here, well, because electric field is, because sigma is same, we see it. So electric field magnitude is same. Both green and orange are directed same direction. So I'm just going to draw arrow twice bigger. That's going to be net electric field, E net, okay? Well, what I'm going to have here, well, because they are same magnitude, opposite directions, they're going to cancel, and I'm going to just put 0 here. Okay, there is no electric field. Well, we do remember that inside of the conductor, there is no electric field. What are we going to have on the right side? Again, same direction, both green and orange arrows, same magnitude, because the sigma is same for both plates. So I'm just going to draw arrow twice bigger than like each of these two, right? And that's, well, on my picture, left arrow, left blue arrow and right are slightly different sides. But, you know, it's really hard to draw anything on a touch screen. Now, I'm just going to calculate what is this net electric field. You see that net electric field on the right and on the left is going to be same, just because it's double of the electric field of one plate, right? So what is net electric field? I'm going to calculate the magnitude, because on the left, it's going to be one direction. On the right, it's going to be opposite direction, right? It's going to be 2 electric fields of one plate, right? Which is actually sigma over 2 epsilon 0 and multiplied by these 2, which is going to give me just sigma over epsilon 0. Now I'm going to plug in my sigma. That's Q1 over 2A 0 epsilon 0. Now, what is idea of the first page? Now they're asking us question. First, do we have the field inside of the conductor? No, there is no field inside of the conductor, right? What is going to happen outside? Guys, if you forget for a second, those two plates are different sides of this conducting sheet, but merge them, these two plates together and draw them like one plate, merge them together into one plate, like this one and this one, draw them as one plate. Then sigma on this one plate is going to be what? The charge Q1 over A1. That's exactly sigma of the one plate, right? If you merge these two together, well, you forget about the zero region because it has no field, nothing, and it's not going to affect anything. Why don't we forget about it? Then we can write down that this is traditional sigma divided over 2 epsilon 0. So net electric field nearby conducting sheet is going to be same as nearby the plane, by the charged plane. If the plane is charged with this the certain density, you see, there is no difference whether you have like this conductor inside or you have nothing inside. And that's idea of the first page. And if you kind of read it without my guidelines, you probably won't understand what they're asking you, where they're guiding you, like what you're supposed to write down. Like on the next page, question D, they're asking you to make this comparison, to compare the conducting plate, which has two sides, right, and the conductor inside, with just charged plane. And you are supposed to see that the field, net field for conducting plate, and if just the plane charged, net field here is going to be what? Sigma over 2 epsilon 0. And that's going to be exactly same sigma, exactly over 2 same epsilon 0. And direction is going to be same. So basically, all conductors can be just considered as charged plates. Now, guys, for like, you can just use all information I told you to fill in the gaps, like in the first page and partially the second page. At the bottom of the second page, there is question E, where they are asking you to consider configuration of two conducting plates and how the charge will be distributed. Remember, guys, the major principle of charge distribution is that inside of the conductor, there is no electric charge. It just cannot stay inside of the conductor. It starts moving somewhere, and the only place where it can rest is the surface, because it cannot move from the surface anyway. The charge does not have like wings to escape the surface. So it moves up to it reaches the surface, and then it stays. For question E, I want you to use this question for a discussion and give me like explanation how the charge is going to be distributed. They give you 3 different positions of charge distribution. When the charge is distributed outside of conducting plates, when the charge is split and half is inside and half is outside, case B, and when the charge is sitting inside of these conducting plates. What I want you to do, I want you to produce a drawing. I'm going to do it for case A. So I'm going to write it down. This is part 1, case E, and the like subcase A. Guys, what I want you to do, instead of drawing conducting plates like they do it in the book, I want you to draw them with bigger distances inside of the conductor. So they have picture looking like this. There's two conducting plates. Here is minus sigma 0, here is plus sigma 0, right? What I want you to do, I want you to draw it next way. I want to put the plates far away from each other. So actually, these are like two sides of this first conducting plate, and these are this and this are two sides of the second conducting plate. So these planes are dividing your space into several regions. I'm going to label them region number 1, region number 2, region number 3, region number 4, and region number 5. So 5 different regions. You see that the charge here, in this case, in case A, sits only on this plate. So I'm going to just label sigma minus sigma here, and sits on this plate plus sigma 0 here. So what I want you to do, draw one set of arrows for each sigma and add them like I was doing on my previous page. So I'm going to do it for negative sigma, but I want you to do it on your own for positive sigma and then find net electric field. After you do this, look what happens inside of the conductor. this part is inside of the conductor, and we know it must be what? Must be E equals 0. But question is it going to be E equals 0 inside of the conductor? Actually, that's going to be the way to determine which of these three configurations, A, B, or C, is going to be actual working configuration for a capacitor. I'm going to draw arrows for sigma 0, and I want you to draw for like second sigma 0, which is positive, okay? And I want you to repeat this for configuration B and for configuration C, same way. So divide your space in 5 regions and draw arrows. For configuration B, you are going to have 4 sets. I'm going to start drawing set of arrows for negative sigma 0. Remember that negative is going to have electric field going into the plate. All arrows are going to be same, all arrows. I'm just going to draw one arrow for each region. And you can label them with E. Again, magnitude of all 1, 2, 3, 4, 5 arrows is same, right? Why do they have different direction? Because the field goes into negative charge, right? So on the left side, it's 1 which goes like to the right, and on the right side there are 4 of them which goes to the left. Why? Because we have 4 different regions here. So what you will need to do to finish my picture here, draw a similar arrows from plus sigma 0, and then see what is the field inside of the plate here and here. If it's not equal to 0, means that it's not a good case for us, because nature makes the field inside of the conductor equals to 0. Then consider same way question B, which is going to have 4 sets of arrows, because there are 4 different positions of the charge. See if the field is 0 in that case inside of the conductor, and then consider case C and 2 sets of arrows, just because two plates are charged, right? And also check it. Make a conclusion which one of these 3 cases is going to be actual case which supports the electric field equals to 0 inside of the conductor. And that's going to be a distribution of a charge inside of the capacitor actually. Okay, for the rest of the tutorial, you can do it on your own. If you have this information, I think it's not going to be too difficult to do it on your own. Okay, okay. So I'm finishing my video. Guys, if you have questions, email to me. Okay, it's hard for me to kind of communicate like using this format.